So now we're at a point where we can go ahead and introduce Faraday's law of induction. So let's say we've got some region right here where we've got a change in the number of magnetic field lines. So let's say the way we're doing it is I got a field going into the screen and the field strength is increasing. Now, in that particular case, it turns out that what will happen is, as I alluded to earlier, we will be inducing an electric field, in this case, where the electric field lines are circles that close in on each other, so they do not start or stop on electric charges, they just loop around, and they would be looping around counterclockwise. Now, this is the same direction as an induced current would have if I had a conductor there following Lenz's law. So it'll look something like that. And let's move that bit right there. Oops. There. So we'll go ahead and induce an electric field like so. Now I alluded to what if I had a conducting loop here. Well, this induced electric field is indeed what is moving the charges around when we were looking at Lenz's law. So I would be inducing, if I had a conducting loop here, I would be inducing a counterclockwise current because the electric field would always be pushing on the charges. Now, the thing is since the electric force will follow the electric field lines, either being parallel or anti-parallel, depending on the sign of the charge carrier, it means in any event that the electric force will always be pushing in the direction that the charge is already going, so the electric force here is continuously doing work. Well, this has to be non-conservative work. And so thus we can talk about having an EMF. Now, why do we know it has to be non-conservative work here? Well, the thing is you would otherwise say that if it were somehow conservative work, then I would be creating a perpetual motion machine of the first kind. Because the electric field would just be continuously shoving charge around, it would be picking up speed forever. That would be a machine that would run forever, and also we could extract energy from it, violating both the first and second laws of thermodynamics. So the energy has to come from somewhere. In this case here, the energy is coming from the fact that the number of magnetic field lines is changing. I'm having to do work somehow to change the number of magnetic field lines. And this is also true in general, because it turns out what matters is that it's a change in the flux. So if I change the area of the loop, I have to somehow do work to change that shape or change the angle or whatever. So anyway, what turns out to be the case is that if I go shove a charge around for one lap, the EMF that we have, which is the work per unit charge that we would be shoving around, will be equal to the time rate of change of the magnetic flux. Now, like I said, you aren't going to have a perpetual motion machine, but we can increase the amount of the EMF. Say if I have a coil of wire, then I could force the charges to do multiple laps. So if I have an N-turn coil, the magnitude of the EMF will be equal to N times the time rate of change of the magnetic flux. So just to give a quick example of that, let's say we have a 1,000 turn solenoid. So remember, a solenoid is just a coil of wire. So we'll say that we have 1,000 turns. And let's say we have a uniform magnetic field that is initially at 1/10 of a Tesla, and whoops, 0.1 Tesla, and we'll let it drop to 0 Tesla in 10 milliseconds. So this could happen if we had, say, something like what's called a magnet quench, where current is suddenly cut off to an electromagnet, and trust me, that's usually really bad things happening. But one of the things that will happen is the magnetic field will drop quite quickly. Let's go ahead and say the diameter of our solenoid is 2 centimeters. So what I would like to know is what is the EMF that we're going to have across the ends of the coil. Well, we can go ahead and use Faraday's law of induction here. So the magnitude of the EMF will be N times the time rate of change of the magnetic flux. Now, the reason we can go with working in magnitude is we can, if we need to know polarity, we can always use Lenz's law to talk about which way we would be trying to shove charges around in the circuit. So for our purposes, it'll be fine just to work in magnitude. All right, so this will be the time rate of change of the B times A times the cosine of the angle. Now here, the plane of our loop is like this, and so our normal looks like that. So that's the normal makes a 0 degree angle with the magnetic field. So cosine of 0 is 1. Now, here the area isn't changing. So since the area is a positive number, I can first note that the change in the product of the magnetic field and the area, if the area doesn't change, is the same difference as the area times the change in the magnetic field. And since the area is positive, I can also pull it out of the absolute value. So this will be N times the cross-sectional area of my coil times the time rate of change of the magnetic field. So the area of a circle, you can write as pi r squared. You can also write it as pi d squared over 4, which is what I'm going to do here. All right, so we have 1,000 turns times pi. The diameter is 0.02 meters, and we'll square that, divide that by 4. So our final magnetic field strength is 0 teslas. Our initial is 0.1 over 100th of a second. And it turns out that this will give you pi volts. All right. So in the last bit here, I've been alluding that Faraday's law of induction and motional EMF are two sides of the same coin. So I'd like to go ahead and motivate that a bit more as I'm sort of tying up loose ends here. So we can go back to thinking about our rail, our conducting bar that was going down conducting rails again. Except we're going to make one change. So here's my bar going down the rails at speed v. Let's go ahead and have a magnetic field that is going into the screen just like before. And before, I went ahead and put a fairly normal resistor across it, and we talked about how much we were heating up the resistor. But here what I'm going to say is, let's make this an infinite resistance. If I make this an infinite resistance, then really we're having no current flowing through here. And now what we've got effectively is just our airplane wing flying through the air. through magnetic field, which we were thinking about earlier. This is something that physicists call the construction of the equivalent problem. Electrically, it makes no difference whatsoever if I just think about an airplane wing flying through a magnetic field, or if I go ahead and put superconducting rails on it, but then attach an infinite load resistor, no current is going to be flowing either way. But what this will do for us is we can say the induced EMF will be the time rate of change of the magnetic flux. So here, whoops, equals. So here, that's, in this case here, as the bar keeps moving to the right, we can see the number of magnetic field lines is increasing, so it'll be a positive number, so I can drop the absolute value signs. So this will be the time rate of change of BA cosine phi, where phi is the angle between the bar and the magnetic field. But here, with respect to time, but again here we'll note that we'll make our cosine 1 because our angle phi is 0. Okay, great. Because the normal to this is going in and out of the screen, because this is my loop here. So the normal to the loop is in and out of the screen. The magnetic field is into the screen, so the angle is 0. Okay. So the magnetic field doesn't change. So what I've got here is the change in the product of B and A, but here the magnetic field isn't changing. So the change in the product of B and A will be the same thing as B times the change in A. With respect to time. But what is the area of the loop? Well, let's go ahead and give this some dimensions. We'll say that this is L to be consistent with the length of our airplane wing before. And we'll just say that this distance that we've gone downrange from our infinite ohm resistor is X. Okay. So this will be B times the change in the product of L and X with respect to time. But L doesn't change, so again it'll be the same deal. The change in the product of L and X is the same thing as L times the change in X. So that's B, L, times the time rate of change of the X coordinate. Oh my gosh, that's the velocity, that's the speed of our bar, BLV, which is exactly what we got before when we did this with motional EMF. And this always has to be the case. So here we have two different avenues by which we can think about the problem. You can either think about by motional EMF, or we can think about by Faraday's law of induction. And we get the same answer either way. And in fact, you will always get the same answer either way. This is because physics has to be internally consistent. So if there are two different ways to look at a problem, and you can find even one situation where the two different routes will give you different answers, then that means that there's something wrong with the model of physics, that model of nature that we physicists have been developing. And that means we would have to go back and re-examine everything. Now it turns out that this is just a flavor for showing the equivalence of the two. The thorough analysis to show that you will always get the same answer in all possible cases, that motional EMF and Faraday's law of induction are the same thing, is more complicated than is suitable for this treatment. But I wanted to give you at least some flavor for the argument there, so that we can see that, yes, if the laws of physics offer you two different ways to think about a problem, you will always get the same thing. I want you to go ahead and take a look at this demo here. So today we're getting a return visit from our friend, the ridiculously powerful magnet. Now what I also have here is an absolutely ordinary copper pipe, the kind you can buy from any big box store.
Now, copper is not magnetic. We can see here it doesn't want to stick. In fact, I can even just drop it nearby. We see it falls normally. Nothing special there. Now, what I'm going to do is I'm going to drop the ridiculously powerful magnet through the copper pipe. I want you to predict what's going to happen there. So go ahead and pause the video and make your prediction. Okay, do we all have our predictions here? Let's see what happens. Well, sure looks like it took an awful long time to fall. So what's going on with that? All right, so what the heck do you think is going on here? Pause the video for a bit and see if you can come up with an explanation for what you just saw. All right, so the name of this phenomenon is eddy currents. Now, when I dropped the magnet through the copper pipe, I don't know if it was the north end down or the south end down. It turns out not to matter. It will just basically turn the whole diagram upside down, but the result will be the same. So we'll say this is the north end here, that's the south end there. And if the magnet were the other way around, like I say, just, I don't know, do a headstand and look at the monitor that way if you prefer. But the result will be the same either way. So let's just draw a few magnetic field lines here and here. All right, so we'll be doing something like this. All right, so now if I am, the way to think about this is think about like little washers, you know, like little thin rings of the copper pipe. Immediately above and below our falling magnet. And actually, let's go ahead and just note that the magnet is indeed falling down. Alrighty. So if I look at a little bit of washer or of copper ring underneath here, so I'm imagining sectioning this copper pipe into a whole bunch of rings. Let's look at this ring right here. As the magnet falls down and it approaches this ring, is the flux through this ring going to go up, go down, or stay the same? Pause and get back with me. So yeah, it's going to go up. So we're going to have an increasing downward flux, which means that we will have to have an upward pointing induced magnetic field, which means that we will have to induce a current in this ring of pipe going like this. And of course, looping back around on the back side. Alrighty, now let's go and take a look at a corresponding ring of pipe above. It's the flux through this chunk of ring here going up, down, or staying the same. Pause and get back with me. Right, here it's going down because as the magnet falls down, more and more the field lines are missing the loop. So we want to reinforce the collapsing magnetic field. So for any of the rings above, we're going to induce a magnetic field pointing down, which means that we will have currents flowing the other way around at the top of the pipe. Okay, but if we think about it, these induced magnetic fields that these currents are making are themselves basically acting like tiny little bar magnets, right? So right here, this would correspond to a north end, and this to the south end of the magnet created by this ring. And here, this would be the north end, and that would be the south end. So here, I got a north next to a south. It's trying to attract the magnet up. And here I have a north next to a north that's trying to repel the magnet up. In both cases, we end up exerting on the magnet a magnetic force pointing up to counter against our force of gravity down. And in fact, because of how ridiculously strong the magnetic field of this particular magnet was, we pretty much just hit terminal velocity almost immediately and fell through the pipe at a constant speed. Alrighty, so in the next series of videos here, we're going to be taking a look, starting to take a look at electronic devices called inductors and transformers that work off of Faraday's law of induction. Catch you over there.